In this video, let us learn to solve question number 1 to 21 from the chapter Current Electricity. The book is Concepts of Physics. In this question, it is asked that the charge which is passing through cross-section of a wire is given as AT square plus BT plus C. We have to find the dimensional formula of A, B and C. We know that here charge is depending upon time. Charge is the function of time, and we know that whenever two or more terms are added, subtracted or equated, each and every term would be having same dimensional formula. That is the characteristics of dimension. So if we take Q, the dimensional formula of Q must be equal to the dimensional formula of AT square, and Q is nothing but charge. Dimensional formula is IT. A, which is constant, we have to find the dimensional formula of, and the T is time, so T to the power 2. Once we simplify it, we will be getting IT minus 1. In the similar fashion, we take Q, dimensional formula is equal to BT, and then BT, that is capital B, T is the time, and then after simplifying we will be getting the dimensional formula of B same as that of current. Similarly, Q is equal to C dimensionally, and then C dimensional formula is nothing but equal to dimensional formula of charge, that is I into T. B part of the question is saying if the numerical value of A, B and C are 5, 3 and 1 respectively in SI units, find the value of current at T is equal to 5 seconds. So now let us put the value as 5, 3 and 1 at the place of A, B and C and differentiate the equation, because here charge is the function of time and we want to get the current. We must apply the formula I is equal to dq upon dt. There are three terms, we have to differentiate them individually. After differentiation, as we know that constant, that is 1, differentiation will be 0, and 5 is constant, will be coming out dt square upon dt. 3 is constant, would come out and it is dt upon dt. Differentiation of power function, that is x to the power n, is nothing but nx to the power n minus 1. So if we take t square, differential term would be 2t to the power 2 minus 1, or 2t simply. So 2t would be multiplied with the 5, it is nothing but 10t plus 3. Now in the question it is asked current we have to obtain at t is equal to 5 seconds. So we are going to put t is equal to 5, it will be 53 ampere. Question number 2, there is an electron gun which emits 2 into 10 raised to 16 electrons per seconds. So number of electrons are given here is 2 is to 10 raised to 16 per seconds, means in 1 second. What electric current does this correspond to? We know that if there is something, charge is flowing across the cross section of a conductor, there would be current. But here charge directly is not given, rather the number of electrons are given. We know that one electron contains the number of, or the amount of charge, which is nothing but 1.6 into 10 raised to minus 19 coulomb. So how much total charge on these many electrons, that is 2 into 10 raised to 16, we need to multiply, and once we get the value of or amount of total charge, we can divide by 1 second, because already in the question it is given per second. So on calculation, the value of current which appears here is 3.2 into 10 raised to minus 3 ampere, or 3.2 milliampere. Question number 3, the electric current existing in a discharge tube is 2 microampere. The current which is given is nothing but 2 micro, means 2 into 10 raised to minus 6 ampere. How much charge is transferred across a cross section of the tube in 5 minutes? Again, if we want to find the charge, we need the formula as Q is equal to I into T, because I is equal to Q upon T as per the definition of the current. So Q we want to find here as I into T. The value of I we can take 2 into 10 raised to minus 6 ampere, and time in SI unit, if 5 minutes we are going to take in seconds, it is nothing but 300 seconds, and after calculation we will be getting the amount of charge which is passing through the cross section is nothing but 600 into 10 raised to minus 6 coulomb, or 6 into 10 raised to minus 4 coulomb. Question number 4 is saying the current through a wire depends on time as I is equal to I naught plus alpha t, where I naught is equal to 10 ampere and alpha is equal to 4 ampere per second. Find the charge crossed through a cross section of wire in 10 seconds. So things which are here, we have already equation I is equal to I naught plus alpha t. The value which is given here for the alpha is 4 and I naught is 10. So equation will be I is equal to I naught, that is 10, plus alpha, that is 4, into t. So this is the equation for the current. We need to find the charge. As we can see here, the equation of the current is function of time. Function of time means as time increases, current increases. Current is not the constant, so that we can multiply by the time and we can get the amount of charge. So now we have to apply the formula I is equal to dq upon dt, and then dq is equal to I into dt. I value we can put here and then integrate. So dq integration will be q, and then value of I if we are going to put here, 10 plus 4t, after integration 10t plus 4 t, integration will be t square upon 2. So after putting higher value minus lower limit, or higher limit minus lower limit, we will be getting the value of charge which is passing through as 300 coulomb. In this question number 5, it is said that the current of 1 ampere exists in a copper wire of cross section 1 millimeter square. So current is given 1 ampere, cross section area is given 1 millimeter square. If we take or change it into SI system, it is 10 raised to minus 6 meter square. And next part is saying assume 1 free electron per atom. Calculate the drift speed of the free electron in the wire. The density of copper wire is given as 9000 kg per meter cube. Actually, this density of copper wire we cannot use directly in this particular question, because if we want to calculate the drift speed, the formula is I upon NaE, where N is number of free electrons in unit volume. That is not given directly in the question, rather they have provided the density of the copper wire, of the copper material. So what first we are going to do, we are going to calculate number of free electrons in unit volume, and then after we can use the formula Vd is equal to I upon NaE. We know that the molecular weight of the copper is nothing but 63.5 gram, or 63.5 into 10 raised to minus 3 kg. That much amount of copper is nothing but 1 mole, and we know that 1 mole of any material contains its number of atoms as 6.023 into 10 raised to 23, that is equal to Avogadro's number. So 63.5 gram or 63.5 into 10 raised to minus 3 kg of copper contains the number of atoms equal to Avogadro's number. So if we talk about 1 kg or unit mass, how much it is? Total number of atoms, that is 6.023 into 10 raised to 23 upon 63.5 into 10 raised to minus 3 kg. Then mkg contains how many atoms? It is 6.023 into 10 raised to 23 into mkg upon 63.5 into 10 raised to minus 3 kg atoms. This m which we have taken here, if we want to calculate n, that is number of atoms in unit volume, it means we have to divide by volume itself. Once we divide by volume, it is nothing but mass per unit volume, and mass per unit volume is given in the question, that is density. So here mass per unit volume, in order to calculate the total number of atoms present in the copper, that is we put rho as 9000 kg per meter cube, and once we calculate this value, we will be getting 8.535 into 10 raised to 28 atoms per meter cube. If you see in the question, it is written clearly that assuming 1 free electron per atom, it means if this is the number of atoms in unit volume, same number of free electrons also will be there in the copper, that is 8.535 into 10 raised to 28 electrons per meter cube. So this value of N we are going to use for the calculation of drift speed, that is N is equal to 8.535 into 10 raised to 28. From the previous calculation we have got current is 1 ampere, area is 10 raised to minus 6 meter square, and the formula which we are having is I upon NAE. So current is 1, N is 8.8535 into 10 raised to 28, and then the area is 10 raised to minus 6, and E, that is electronic charge, is 1.6 into 10 raised to minus 19. Once we simplify, it is 10 raised to minus 3 upon 8.8535 into 1.6. After multiplication it is 14.16, and after division 1 by 14.6 it is 0.0706 into 10 raised to minus 3 meter per second, or 0.07 millimeter per second. That is the drift speed of electron inside the copper wire. Question number 6 is given a wire of length 1 meter and radius 1 millimeter. What is given is length of wire is given as 1 meter, radius is 1 millimeter, it means 0.1 millimeter, it means 10 raised to minus 4 meter, and the resistance is given 100 ohm. Question is find the resistivity of the material. So to get the resistivity, we have the formula as R is equal to rho into L by A, where A is area. Area we don't know because it is not given in the question, it is given radius. So if we take area, because the cross section is circular, it is pi r square. Pi is 3.14, r is 10 raised to minus 4, on squaring it, it is 10 raised to minus 8. And then we will be using the formula R is equal to rho into L by A. We have to find the resistivity, so we'll try to find the formula in terms of rho, that is rho is equal to Ra upon L. We put the value R as 100, area as 3.14 into 10 raised to minus 8, L as 1 meter, and after calculation we will be getting it as 3.14 into 10 raised to minus 6 ohm meter. Question number 7 is saying that a uniform wire of resistance 100 ohm is melted and recast in a wire of length double that of the original length. What would be the resistance of the wire? One thing we know, even if wire is stretched to double of its length or it is compressed to certain limit, the volume remains unchanged, and that is the conserved particle over there, or conserved nature over there. So what we are going to have here as per the question is, first resistance, that is R or R1, is given as 100 ohm, and then length L dash is equal to 2L, that is becoming double. So now let us first take the formula of R in terms of rho, because material is same, rho is not going to change, it would be constant. So R is equal to rho into L by A. Now if we multiply and divide RHS by L, it is rho into L square upon AL. AL is nothing but volume. So R is equal to rho L square upon volume. After this, what we are going to have here is, we can take L, or we can calculate R dash, that is the new resistance, as rho 2L, that is the length is becoming double, that is L dash square or 2L square upon volume. So on squaring it, it is 4L square, or 4 times to the value of R that we have already obtained here, that is 4 into R. So initial resistance was how much? Initial resistance was 100 ohm. Now the value of new resistance is going to be 400 ohm on stretching the wire or recasting the wire double of its initial length. Question number 8 is saying, consider a wire of length 4 meter and cross section area 1 millimeter square carrying a current 2 ampere. If each cubic meter of the material contains 10 raised to 29 free electrons, find the average time taken by an electron to cross the length of the wire. So what all things are given? Length of the wire is given, that is 4 meter. Number of free electrons that is per unit volume is 10 raised to 29, and then area is given 1 millimeter square. On taking it in SI unit, it is 10 raised to minus 6 meter square, and then current is given 2 ampere. We have to find the time taken by an electron to cross the length. For that we need drift speed, because electron would be traveling or moving with the drift speed inside the conductor. So to calculate the time, we can apply the formula length, that is 4 meter, upon drift speed. So drift speed formula is Vd is equal to I upon NAE. To calculate the time, we have length upon drift speed, and length is how much? As per the question it is given 4 meter we will be putting, and Vd is I upon NAE. So if we take it in terms of time, length, NAE, the formula is T is equal to length into NAE upon I. Now length is 4 meter and N is 10 raised to 29, area is 1 into 10 raised to minus 6, E is 1.6 into 10 raised to minus 19 upon I, that is current is 2 ampere. On simplifying, we are getting T is equal to 3.2 into 10 raised to 4 seconds, or we are getting 32,000 seconds, or we are getting 32,000 upon 3600 hours, or finally in hours we can calculate 8.89 or 8.9 hours is the time taken by an electron to cross 4 meter of length when the current is 2 ampere. Question number 9. What length of copper wire of cross section area 0.01 millimeter square will be needed to prepare a resistance of 1 kilo ohm? Resistivity of copper wire is given. So what all things are given? If we see here, area is 0.01 millimeter square. If we want to change, it will be 10 raised to minus 8 meter square. Then resistance is given 1000 ohm, and rho, that is 1.7 into 10 raised to minus 8 ohm meter. What we have to find? We have to find what length of a copper wire of cross section will be. Length we have to find. So R is equal to rho into L by A. If we want to take the formula in terms of length, it is L is equal to RA upon rho. The value is given, R is given as 1000, the area is 10 raised to minus 8, and rho is 1.7 into 10 raised to minus 8. So L is equal to 1000 upon 1.7 meter, or 588.23 meter, or approximately we can say 0.6 kilometer. That is the length of the wire required for this particular question. In this question, it is said that there is a figure of length L having circular cross section. The radius of cross section varies linearly from A to B, as you can see in the diagram. At one end it is A, at the other it is B, and the resistivity of material is given. We have to find the resistance of the conductor. B minus A we can consider much lesser than 1. So what we are going to take here, the length is L, here the radius is A, here the radius is B as per the question. If we can take two parallel lines in order to demark A and B parallelly, we can get here theta, that is the inclination, that will be helpful in order to compare the similar triangles. At a distance x, now what we are going to consider one small cylinder, because we can consider that this particular material can be built by infinite number of cylinders, where one cylinder length we are going to take here as dx. Once we get the value or resistance for that cylinder, we can integrate the same value from E to B. So basically we are going to find the resistance of this small cylinder having radius y and thickness dx, or length dx. Here this particular section will be y minus a, and this is b minus a at distance L. So if we have the resistivity rho, length L, cross section area A, we know that the resistance is nothing but rho into L by A. But here now we are going to consider again, as I said, that cone is made up of infinite number of cylinders. We are going to consider one cylinder of length dx. What is the resistance? Small resistance dr is equal to rho dx by a. That we are going to take as equation 1. Now, total resistance, if we want to calculate, we have to integrate dr from a to b. That we are going to take as equation 3. Now, the resistance for an element of radius y, as you can see at distance x, and length or the width is taken as dx, that particular resistance will be dr is equal to rho dx upon area at that particular point. So what is the area at that particular point? Pi into radius square, that is pi into y square. This we are going to take as equation 3. Now, from the diagram, if we compare two similar triangles which are having the common angle theta, we can write b minus a upon l is equal to y minus a upon x. That sides ratio will be same. And on simplifying, it is x b minus a is equal to l y minus a. We are going to differentiate this term with respect to x. So on differentiating, what we are getting here is b minus a is equal to l dy upon dx. A would be 0, differentiation of a would be 0 because it is constant. The other side it is dx upon dx, it is 1, and b minus a only would be left. Other part would be the differentiation of b minus a, that would be 0. So on differentiation, it is b minus a is equal to l dy upon dx, or dx is equal to l dy upon b minus a. Now, if we take the equation here 1, 2 and 3 from the previous para, we can take the value of dx here, and from equation first, or in equation first, we are going to put the value of dx as l dy upon b minus a. So rho dx upon pi y square, rho dx is l dy upon b minus a pi y square, and then we are going to simplify, it is l dy upon b minus a pi y square. Now from equation second, this particular term has to be integrated from a to b. So now dr we are going to integrate, it is r, RHS part we are going to integrate from a to b, which all parts are constant would be taken out. It is rho l upon b minus a into pi. So we have to integrate basically 1 by y square with respect to y. We know that integration is minus 1 by y, and we have to put the upper limit as well as lower limit. Because negative sign is there, we can put the limit as lower minus upper, and it is 1 by a minus 1 by b. So once we simplify this, LCM will be AB, and then it is B minus A, B minus A term would get cancelled, and the resistance which comes out here is rho L upon pi into AB. In this question, it is said a copper wire of radius 0.1 millimeter and resistance 1 kilo ohm is connected across a power supply of 20 volt. How many electrons are transferred per second between the supply and the wire at one end? Write down the current density in the wire. So what all things are given in the question? First, it is given radius is 0.1 millimeter. So area would be pi into 10 raised to minus 8 meter square. And then resistance is given 1000 ohm and voltage is given 20 volt. We know that as per Ohm's law, what is the amount of current, that is voltage upon resistance. If we apply this formula, we will be getting current as 0.02 ampere. Once we get the amount of current as 0.02 ampere, we can equate this particular current with charge per unit time, and charge we know as per quantization it is nothing but Ne. So I is equal to Ne upon time, or because we have to find here how many electrons are transferred per second, it means we have to find N upon T, that is number of electron transferred per second, nothing but I upon E, and I we have here as per the previous calculation 0.02 0.02 and E is 1.6 into 10 raised to minus 19. After calculation, we will be getting, because we know 1 by 1.6 into 10 raised to minus 19 is nothing but 6.25 into 10 raised to 18. So same value we can take here as 1.25 into 10 raised to 17 electrons per second on substituting T is equal to 1 second. Now next part of the question, that is B, it said write down the current density in the wire. So to calculate the current density, what we require is J, that is current density, is equal to current per unit area, and current here is 0.02, area of cross section is 3.14 into 10 raised to minus 8. On uh, simplifying it, it is 2 upon pi, or 0.637 into 10 raised to 6, or 6.37 into 10 raised to 5 ampere per meter square is the final answer. So current density is 6.37 into 10 raised to 5, and the number of electrons which are passing per second is 1.25 into 10 raised to 17. Question number 12 is calculate the electric field in a copper wire of cross section area 2 millimeter square. So what things are given here in the question is area is given 2 millimeter square, that is 2 into 10 raised to minus 6 meter square. Current is given 1 ampere. The resistivity of copper wire is given as 1.7 into 10 raised to minus 8 ohm meter. We have to calculate the electric field in the copper wire. So electric field, how it is related to the Ohm's law that we are going to have, because V is equal to IR we know, and R is equal to rho into L by A. So if you want to write the same formula again, we can write V is equal to I. At the place of R we can write rho into L by A. Why we are taking here voltage? Because electric field is nothing but voltage per unit length in terms of this particular question. So here electric field, if we want to take voltage per unit length, and voltage as per this particular formula, it is I rho L by A upon L. Once we simplify this, L would cancel, and then it is I into rho upon area. I is given 1 ampere, rho is 1.7 into 10 raised to minus 8, and the area is 2 into 10 raised to minus 6. Once we simplify it, electric field which we are going to get here is 1.7 upon 2 into 10 raised to minus 2, or 1.7 upon 2, it is nothing but 0.85. If we take 8.5, it is into 10 raised to minus 3 volt per meter. Question number 13. A wire has a length of 2 meter and resistance 5 ohm. Find the field existing inside the wire if it carries a current of 10 ampere. So what all things are given here in the question? R is 5 ohm, L is 2 meter, and current is 10 ampere. To get the value of electric field, again we are going with the same formula, Ohm's law. V is equal to IR, E is equal to V by L, it means IR upon L, and all the values are given here. Like I, the value is given 1, R is 5, L is equal to 2, so it is 5 upon 2, or uh, 50 upon 2, or it is nothing but 25 volt per meter. So value of I after putting 10, L2, R5, we are getting it as 25 volt per meter. In this question, it is said the resistances of an iron wire and a copper wire at 20 degrees Celsius are 3.9 ohm and 4.1 ohm respectively. At what temperature will the resistances be equal? Temperature coefficient of resistivity of iron is given and copper is given. So what all things are given? Let us see in two parallel manner. That is iron, the temperature first. For copper, temperature first is given 20 degrees Celsius, and then initial resistances are 3.9, 4.1. For iron, the uh, resistivity temperature coefficient of resistivity is 5 into 10 raised to minus 3. For copper, it is 4 into 10 raised to minus 3. We have to calculate the resistance after temperature T2 when they are going to be same. Same value that is not given, but we can consider that they are going to be R, then what is the final temperature? So for that we are going to take the formula as R is equal to, or R2 is equal to R1 1 plus alpha delta T. So for iron we are going to write R is equal to R1 1 plus alpha of iron and T2 minus T1. Similarly we are going to write for the copper as well. Because both are same, after a particular temperature T2 we are going to equate them. And R1 value for both are given, so we are going to put the value as well, 3.9 and 4.1. Once we multiply inside, it is 3.9 plus 3.9 alpha iron delta T is equal to 4.1 plus 4.1 alpha C, that is for copper delta T, and then we are taking the 3.9 and 4.1 one side, the difference is coming as 0.2. Delta T we are going to keep common, and we are going to now put the value of alpha I and alpha C, that is for iron as well as copper. So once we put the value like 5 into 10 raised to minus 3 and 4 into 10 raised to minus 3, 10 raised to minus 3 we are going to keep common. Now if we multiply 5 into 3.9, it is 19.5, 4.1 into 4, it is 16.4, and the difference will come as 3.1. If we are sending 10 raised to minus 3 right hand side towards, it is 0.2 into 10 raised to 3 or 200. So delta T is equal to 200 upon 3.1. It is nothing but 64.5 degrees Celsius. And we know that delta T is nothing but T2 minus T1. So T2 is equal to 64.5 plus T1, and T1 value is given 20 degrees Celsius. So on adding, it is 84.5 degree Celsius. Question number 15 is saying that the current in a conductor and the potential difference across its ends are measured by an ammeter and a voltmeter. The meters draw negligible current. The ammeter is accurate, but the voltmeter has a zero error. That is, it does not read 0 when no potential difference is applied. It may be ahead to 0 or maybe before 0. Calculate the zero error if the readings for two different conditions are given. I1 V1, I2 V2, these values are given. What is I1, what is V1, what is V2, what is I2, that is given in front of you. So I1 is 1.75 ampere, then V1 is 14.4 volt, then V2 is 22.4 volt, and I2 is 2.75 ampere. So let us now consider that the voltmeter is having some initial readings already, that is the error part, that we are going to take as V0. So if we apply again here Ohm's law, we know that delta V is equal to IR, or potential difference is equal to I into R. Potential difference, if we take for the first one and the second one, first condition and second condition, and we are going to divide them, we will be getting one comparison as delta V1 upon delta V2 is equal to I1R upon R2R. R1, I1R, I2R, RR would get cancelled here, and then it is V1 minus V0, V2 minus V0 is equal to I1 upon I2. And then if we put the value here, 14.4 minus V0 upon 22.4 minus V0 is equal to 1.75 upon 2.75, and then if we are multiplying this LHS RHS by 4, what we are getting, the simplest form of this particular equation is 14.4 minus V0 upon 22.4 minus V0 is equal to 7 upon 11, and then cross multiply. After cross multiplying, what we are going to get here is 11 V0 minus 7 V0 is equal to some part coming after subtraction, and it is nothing but 1.6, or V0 we are going to get 1.6 upon 4, and that part is nothing but 0.4 volt. So voltmeter is having already some error as 0.4 volt in this particular voltmeter. Question number 16 is saying that in the figure there is EMF of batteries E, internal resistance is R, and the voltmeter has high resistance, very high resistance, and ammeter also has some resistance. The voltmeter reads 1.52 volt when the switch S is open. Switch S is open, voltmeter is giving some readings. As we know that when we are going to measure the EMF of a battery, there should not be any load resistance. So S is opened, voltmeter is showing 1.52 volt. It means that is nothing but EMF of the battery. When S is open, now when the S is closed, the voltmeter reading drops to 1.45 volt, and the ammeter also is going to read certain amount of current. Find the EMF and internal resistance of the battery. So as I said, when S is open, the current would circulate through loop A, B, C, D, A, but the other loop like A, D, E, F, A current will not be there. So internal resistance is very small compared to the resistance of voltmeter. The voltage drop occurs completely across the voltmeter. So this voltage drop will be measured in the meter, and it is nothing but equal to EMF or almost equal to EMF of the cell, which is 1.52 volt. Now second condition, what is given here in the second condition, which we can understand, is V is equal to E minus IR. That is terminal potential difference is E minus IR. So V is 1.45, E is 1.52, current is 1 ampere, R we can calculate easily as 0.070. The question says potential difference between the terminals of a battery of EMF 6 volt and internal resistance 1 ohm drops to 5.8 volt when connected across external resistor. We have to calculate the external resistor. So what all values are given? As per the question, we can see EMF is 6, internal resistance is 1 ohm, terminal potential difference is 5.8 volt. We have to calculate what is the external resistor. So now we know that the formula which we can get the current from the EMF and the total resistance is I is equal to E upon capital R plus small r. We are going to put the value of E, we are going to put the value of internal resistance. Now this is the value of current. Now the relation between the terminal potential difference and EMF is V is equal to E minus IR when current is drawn from the battery. So V is nothing but 5.8, which is terminal potential difference, E is 6 minus I is 6 upon capital R plus 1 into small r is 1 ohm. We are going to simplify this equation as 6 upon R plus 1 is equal to 6 minus 5.8. That subtraction will be equal to 0.2, and then we are multiplying this 0.2 into R plus 1. It is equal to 6, and once we get this equation, we are going to have 6 upon 0.2 is equal to R plus 1. This value is nothing but 30, so R plus 1 is equal to 30, and then R is equal to 29 ohm is the resistance of the external resistor. Question number 18 is saying the potential difference between the terminals of a 6 volt battery is 7.2 volt when it is being charged by a current 2 ampere. What is the internal resistance of the battery? So what is given here? That EMF is given 6 volt. The potential difference, terminal potential difference while charging is 7.2 volt. And the current is 2 ampere. We have to calculate the internal resistance. We can use the same formula, but for charging it is nothing but E plus IR. For discharging means when current is drawn from the battery, it is E minus IR, but when current is given to the battery, it is E plus IR. So V is 7.2, E is 6, 2 into R, and then after calculation we will be getting internal resistance as 0.6 ohm. In the question, it is saying that internal resistance of an accumulator battery is of EMF 6 volt is 10 ohm when it is fully discharged, but when it is charged, the internal resistance decreases to 1 ohm. The battery is in its completely discharged state, is connected to a charger which maintains a constant potential difference of 9 volt. Find the current through the battery. In A it is saying just after the connections are made, means when it is completely discharged, and B after a long time, it means when it is completely charged. So let us take the given part for two conditions, discharged and the charged. It is E is equal to 6 volt, E is equal to 6 volt, R is equal to 10 ohm and then R is equal to 1 ohm. Potential difference in both the senses will be 3 volt. In the first situation, if you are going to calculate the current, it is 0.3 ampere as potential difference upon resistance, that is 10 ohm when it is completely discharged, and in case of charged the internal resistance decreases to 1 ohm, so the current will be 3 ampere. Question number 20 is saying that looking at these two diagrams or the circuit diagrams, we have to find the ratio of I1 and I2. There are three conditions when R is equal to 0.1 ohm, R is equal to 1 ohm and R is equal to 10 ohm. So first let us find the ratio I1 upon I2 in terms of R, and then in terms of total R equivalent, that is total resistance. Then the A conditions, B conditions and C conditions we can entertain separate. So here if you see the first diagram, the cells are connected like positive negative, it is series combination. Here both positive together, both negative together, it means parallel combination. So series combination, we know that the effective EMF is nothing but addition of individual EMF here. So it is 6 plus 6 or E1 plus E2. In parallel combination, potential remains the same. So when potential remains the same, it is 6 volt and 6 volt. So here it is 12 volt and here it is 6 volt. Now R equivalent in series combination is the algebraic sum, that is 1 ohm plus 1 ohm. So it is nothing but internal resistance is 2 ohm, and here it is just half, because in parallel combination it is 1 by R1 plus 1 by R2 is equal to 1 by R equivalent. So it is R by 2, that is 1 by 2 or 0.5 ohm. So these are the basic calculations from both the diagrams. Now here in the first diagram, if we want to calculate the current, it is E upon total resistance, that is capital R plus small r. Here it is I1 is equal to E 12 capital R plus R, and then here I2 is equal to 6 upon capital R plus R dash. Now we are going to get the ratio, that is I1 upon I2. So 12 upon 6, it is 2, and then R plus R dash upon R plus R. Now this formula we are going to use for A now, where the R is 0.1 ohm. So once we put the value, we are going to get the ratio as 1.2 upon 2.1, that is 0.57. For B part, R we are going to keep as 1 ohm. So 2 into 1 plus 0.5 upon 1 plus 2. So 1 plus 0.5 is 1.5 into 2, 3 upon 3, it is nothing but 1. Then for C we are going to have again R is equal to 10 ohm, then 2 into 10 plus 0.5, nothing but 21 upon 10 plus 2 is 12, and the ratio is 1.75. Now question number 21 is basically asking about mixed combination of cells. The question is said that N is nothing but N1 N2 identical cells, each of EMF E and internal resistance R. Supposed N1 cells are joined in series. So let us take this N1 cells are joined in series, and like this N2 rows are connected in parallel. Like this N rows are connected in parallel as per the question. So total number of cells will be N1 into N2. The question is find the current in the external resistance. So now let us connect one external resistance here. The combination is made in such a way that external resistance is here. So before going to the current, we need to know what is the EMF of one row, that is addition or algebraic sum of individual EMF E plus E up to N1 terms, it is N1 into E. Then what is the effective EMF of the combination, because like this many rows are there. So for effective EMF we are going to take, because in parallel combination we know the EMF remains the same. So for first N1E, second N1E, or effective also it is nothing but N1E. Now let us calculate internal resistance of one row. It is R1 plus R2 plus R3 up to N1 terms, because each cell is having same amount of resistance. It is R plus R plus R up to N1 terms, so it is N1 into R. Now N1R, N1R, N1R many times, means N2 times, they are connected in parallel combination. So for parallel combination we have the formula 1 by Rp is equal to 1 by R1. We are using same up to N2 terms. So after using this formula we will be getting the internal equivalent resistance of the circuit as N1R upon N2. So this is the internal or total internal resistance. Now total resistance of the circuit is internal plus external, that is capital R plus N1R upon N2. So now we have effective EMF, now we have total resistance, we can calculate the current. So current is equal to total EMF upon total resistance N1E upon R plus N1R upon N2. This could be the answer, or if you simplify it is N2 N1E upon N2R plus N1R. Now one more part is there. Assuming that N1 and N2 can be continuously varied, find the relation between N1 and N2, R and R, for which the current in external resistance is maximum. So here I can be maximum when the denominator is minimum. The denominator is N2R plus N1R, and if we apply the maxima and minima theory, we would be reaching to the combination calculation of this combination is R is equal to N1R upon N2, or N2R is equal to N1R. It means total internal resistance when is becoming equal to the total external resistance, the current in mixed combination is happening maximum. Thanks for watching.